Welcome back, students. So today we will be talking about dislocations. So we have seen so far that plastic deformation takes place in the material if you keep applying a higher and higher stresses. However, this plastic deformation at first people thought happens by complete cleavage of bonds or between two different planes, and then the planes slip apart on along each other. However, the experimental observations were very different. So what were these experimental observations? There were two main experimental observations and which were contradictory in nature. One is called the weakening of crystals and the other is called strengthening or work hardening of metals and alloys. So these two observations made people realize that the deformation does not take place like that, and there must be some other mechanism operating. And as you would see, I will introduce some names who discovered or who hypothesized this concept of dislocations. And what is very intriguing is that they hypothesized in 1934, which itself was after quite some time of discussion in the scientific groups. And the real observation of dislocations was done much later. It was done sometimes in 1950s. Okay, so with this small brief introduction, let's start our today's lecture. So like I said, there were different scientists who contributed to the discovery of dislocations. So who were these people? So let me, it will be very useful if you know the names. So the names are Polyani Mihaly, Egon Orovan. So these two worked together and they primarily worked on the theory or trying to explain weakening of crystals. And then there was also G.I. Taylor. We very well know Taylor hardening, or heard of this term, Taylor hardening. So he worked on the other concept or trying to explain the other observed phenomena, which is strengthening or work hardening of metals. We will explain those in a couple of slides. So the first theory was about weakening of crystals. And the second one was strengthening of work hardened metals alloys. So this one, like I said, was done in the year 1934, and this itself happened after a lot of refinement, where people postulated the theory and then refined it further until in 1934 we obtained what is now called as theory of dislocations. So here the theory was postulated in 1934, but the observation was made much later by Bolman, group of people particularly led by W. Bolman. And this was in the year 1957. They used TEM, transmission electron microscopy, to first observe dislocations. So you can Google through the internet and for some dislocation videos and images which have been taken from TM, and you would see that these dislocations appear like line and more like very thin lines starting from one point to and ending at another point. And this kind of observation is made in TM. So what is the two theory that led people, or two observation? Actually, this will also help you understand how the science works. So people made these observations and then they wanted to explain it, And in the process, they explained it using this phenomena or this concept of dislocations, which was not observed until then because technology of TM was not developed until then, which came up only in early 1950s. And once technology caught up, then people were able to prove and show that yes, indeed, there is something like dislocations. So overall, you can see this is also study about how science works. Okay, so now coming to what is the two theory that or two phenomena that people were trying to explain. So the first one is weakening of crystal. So let's say that you take a bar of single crystal metal. Okay, now earlier understanding was that when it is deforming, basically the whole plane is shearing against each other, and therefore this whole bond, the atom, if there will be atoms over here and they are bonded with atoms on this side, so all the atoms must move with respect to each other. So if that is the theory, then let's look at how much stress would be required for the atoms to move. So let's say that you have, so let me just push this figure a little bit lower because I need to draw some atoms over here. Let's say we have two different layers shown over here. So this is one layer. So here will be another atom for this layer. And there is another layer over here. So this is in the center. This layer, in this layer, the atoms are from the point of view where we are looking at, this is in the center of these two atoms. So this is layer 1 and this is layer 2. Now, if we really think that the whole layer has to move, so it would mean that this layer of atoms must move across this, and therefore there is also one atom over here. So this one, let's say, moves. So this one, if you look at now, what will be the energy plot for this particular atom? So right now, this is the equilibrium position for this particular atom. So let's draw this energy plot with respect to this particular atom. So when it is in its equilibrium position, that time it has the lowest energy. Now, if I try to move it a little bit over here, so somewhere over here, its energy keeps on increasing. Now I bring it over here. It is somewhere in between these two atoms. So energy is highest because this is the most unstable position. And again, if you keep moving it this direction, then again, when it comes back to this position, this is again an equilibrium position. And therefore it will be in equilibrium and the lowest energy state. Now, if this is the energy plot, how would the force which is required to move the atoms along this particular plane would look like? So we know that force is basically the first derivative of energy. So we differentiate it and we will be able to get the energy plot, and which is shown in over here. So this is force, and in both these this plots, this is x. So now over here, if you look for the original position of the atom where the energy is lowest, force is 0. Again, when it comes back to this position, then again the force would be equal to 0. So these are the two the positions where the atom is in equilibrium, and hence over there the force acting on it is 0, force required is 0. But if you want to move it from here to here, then there would be some force required. So let's say this direction, the force that is being applied is shown by negative. So in somewhere over here, when it reaches one about, so let's say that this whole length is b. So when it reaches B by 4, then the atom is over here and it has the maximum amount of force required over here. Now, if you keep moving again towards this, somewhere over here, so it has equal amount of pull from both the directions, and therefore the force is again 0. But this is an unstable equilibrium. If you push it a little bit on this side, the atom would move to this side. If you push it a little bit to this side, the atom will move to this particular position. But as long as you are at this particular position, it is the total amount of force required is 0 and it is unstable equilibrium. And if you again keep moving it, then the force is now acting on it on the other direction, and eventually it will go to a peak value again, and this will be at, with respect to this will be B by 4. This is again B by 4, and this position, which is the minima, energy minima over here, this is again B by 4. So this is how the energy varies, and this is how the force varies. And if we look at this force, this is also how the stress would act, which would mean that we can say that this is how force or shear stress tau acts, and therefore we can write the equation for the stress like this: tau equal to tau max, because it is sinusoidal. So let's say this is the maximum. So this is tau max sine 2 pi x by b. So b is the overall length, and if you keep moving by the distance x, therefore it varies like this: 2 pi x by sine 2 pi x by b. This is the usual form for a sinusoidal wave, where tau is the applied shear stress, tau max is the max of the shear stress, maximum shear stress, which also means that if you are able to apply this much, minimum this much of stress, then you can keep moving the atoms or the planes up away from up past each other, and therefore you can cause deformation. So in other words, this also represents the theoretical strength of crystal. X is equal to distance atoms are moved. And B is the distance between equilibrium positions. So this is the equation where we will start. This is our tau equal to tau max sine 2 pi x by b. Now, when we are doing the deformation, let's say at the very beginning, the x would be very small, and therefore for x much less than b, we can say that this equation can be approximated as tau sorry, now it is no more sign. We can directly say 2 pi x by b. And over here, x by b is nothing but shear strain. So this becomes tau max times 2 pi times gamma, which is the shear strain. But then we also know that tau is given by G, which is the shear modulus, times gamma, and therefore we can equate these two equations, and we have tau max into 2 pi times gamma. Now the strain is same on both the side, and basically it is the same quantity, and therefore we have a relation or an equation which defines the value of tau max, which is equal to G by 2 pi. Now this is a very, very rough calculation, but we have obtained some value, and if we had taken a more appropriate representation of energy and the shear stress, so for the more appropriate form of this curve, as you would see in some books, is like this. And therefore there will be some variation, and based on that also people have calculated what should be the maximum shear stress or theoretical strength, and people have found that using more realistic expression, people have obtained that tau max is equal to G by 30. Okay, so this should be your, and this is approximately G by 6. So somewhere in the G by 6 to G by 30 should be your shear strength of the material. Now let's compare it with how does it compare with experimental values. So for example, aluminum, here let's write G by 2 pi in megapascal and experimental strength. So the G by 2 pi for aluminum should be 4200 megapascal, meaning this is the amount of stress that you need to apply for the material to plastically deform, or somewhere close to this. This should be the yield strength of the material. On the other hand, what is the yield strength that we obtain for a single crystal? For silver, so we are talking about single crystal, so yield strength is not really an appropriate term here. It is the minimum critical shear stress required for deformation of the single crystal. For silver, it should be 4800, and what we get is 0.4 to 0.5. So even if you take this as G by 6 as a exaggeration, and you go for G by 30, which would mean divided by 5, but still what we see that we are orders of magnitude away. So this is the experimental strength, and this is what theory predicts based on assuming that this is how the deformation is taking place by slipping of planes past each other, which clearly implies that our assumption is wrong. So which assumption is wrong? Most likely that is not how the deformation is taking place. This is not how the material is deforming. So just to further emphasize that, let me put some more examples here. Copper, 7700 should be the theoretical strength, and what we get is 0.5 to 3. Even if you go for nickel, which has much higher theoretical experimental strength, which is of the order of 3 to 5, but theoretical strength is even higher, 12,000, meaning 12 gigapascal. As you just imagine, if we had really materials like this, it would have been really good from some point of view, but then you would also realize later on, when you understand the importance of dislocation, that it would also have been bad for us. So what it clearly emphasizes is that our assumed model of deformation is incorrect. Moreover, if you look at the value of flow stress as a function of what is called the dislocation density, of course we have not yet defined it, but if you look at it now, just going a little bit ahead of ourselves, so this is how it looks like. We are on the x-axis. we have increasing dislocation density, and on the y-axis we have flow stress. So when the dislocation density is very low, then the flow stresses are very high. In fact, it can reach the theoretical values that we just talked about. But in general, annealed polycrystal would be somewhere over here, which would have 10 to the power 14 per meter cube of density of dislocations. Somewhere here, you would have high quality single crystals. And here you will have what is called as whiskers. So these are mostly free of dislocations, or nearly free, I should say. So when you don't have dislocations, then the flow stresses are very high, orders of magnitude higher, close to the the theoretical strength that we have come to expect. On the other hand, if you keep increasing dislocation density in this direction, then what we get are strained or work hardened alloys. So just imagine that if the deformation was taking place just by shearing of the planes, then why applying a strain in the material should increase its strength? This is also evident in our uniaxial tensile stress strain curve. If you remember the uniaxial stress strain curve, then it looks something like this. So somewhere over here, we have plastic deformation that begins. And as you keep increasing strain, then we see that the flow stress required is higher and higher, which is also expressed by the relation power law hardening behavior, which clearly shows that as strain increases, flow stress increases. But if it were just a shearing of the planes, why should the flow stress increase? It doesn't make sense. Therefore, again, this emphasized to Taylor that there must be something more than we understand. And based on that, together they came up with the model of dislocations. And when you have a dislocations, so a strain hardening, what is happening is dislocation density is increasing, and from an annealed material, which is somewhere over here, to this particular point, dislocation density again increases, and here you get a much higher strength. Of course, it is nowhere close to the whiskers, but it is much higher than the annealed material, and that is why you see that most of these sheet metals that are used are in the rolled condition, because in the rolled condition you get higher strength in the material. So this is what is strain or work hardening, which cannot be again explained by our earlier model. So these two things clearly emphasize that there must be some other mechanism for deformation, and hence the two people, Poliani and Orowan, worked on theory of dislocation based on the observation that the theoretical strength and experimental strengths do not match, and Taylor saw that when you deform a material, when you do some metal working on it, then their strength increases. So again, he emphasized or hypothesized that there must be something else, and therefore he came up with the concept of what we now call as dislocations. And so though together these three are credited with the theory of dislocations. So now we have talked about dislocations. Let's quickly take a look at how would the dislocations look like, not dislocations, but its artifact. How would you just by looking in optical micrograph or somewhere, how can you say that yes, dislocations are there? And one quick visual proof for dislocation is obtained if you slightly deform a polished material. So let's say you take a polished surface, okay? So you take a polished surface and therefore the atoms inside it are very well arranged, and they are, and from when you look from the top, it will look like a very smooth surface. But now let's deform it a little bit. For example, you may compress the surfaces, and therefore what will happen is that there may be certain slip planes, and because what we will later introduce are dislocations move, and they move in steps, causing step rises. So one step would be equal to the distance of atoms, so it will rise like this, this one, and when there you will have tens and thousands of this, then it will become observable to a naked eye, and what you would see is something like step. So this step is not by just one layer of atoms. It is actually, if you are able to observe it, it is most likely being formed by tens of thousands of such dislocations accumulating and causing or making this very large step. And therefore it will, this is a slip line. So this is a slip line where dislocations have moved and formed these steps, and therefore you have so I have not drawn it to the same scale, as you can see, because I wanted to emphasize the fact that the steps are not just one layer of atoms, but several layers of atoms. And this is a SEM micrograph, and here what you see, these lines, these are basically slip lines where tens of thousands of dislocations have accumulated, and when they ended up on the surface, you were able to see a large step. So these were not happening just along this direction, but they were also happening along this direction. So eventually it becomes so large that we can observe it with naked eyes, and we can see it like this. If you polish it again, then again it will go away, and then again if you deform it or cause any other way, another type of deformation where dislocations have to move, which will eventually come to the surface, and therefore you would be again able to see these. So if you keep polishing again and again, it will keep disappearing, and if you keep deforming again, you will see again, and this will also be observable in your tensile samples. So when you are doing the tensile samples, you have polished it very cleanly, very nicely. Now after some amount of deformation, let's say after 5% deformation, just look at the surface very closely and you would be able to see those slip lines. But there you have to be a little bit careful, because over there you are not talking about one single grain, but there are multiple grains. So you will have to look closely so that you are looking inside one particular grain. But these slip lines may also be, basically this will happen, the slipping will happen across the grains, and so overall you would see that these will cross the grain boundaries and across the grains. So eventually you would be able to see it throughout your bulk sample. So with that, we will come to an end for this first very initial introduction of dislocation, or basically discovery of dislocations. Thank you.